Hello everyone. Am I audible?
Yes, sir.
Good evening, sir.
Good evening. Good evening to all. So welcome to the week 5 of the problem solving session in matrix analysis and applications. So as usual in this session I'll explain some of the sample problems that will help you understand the concept better and solve the assignments by your own. Okay, so there are 5 members. I think we should wait for a couple of minutes for others to join and then we'll start. Okay, so let's start. So question number A. You have given the two matrices A and B, complex reciprocity matrices, such that A star is same as A star. That is, A is normal and B is normal. Then which of the following is true? They have asked which is true. So which one do you think is true? Given that A and B are normal, which one of the four matrices they are given are normal? So I think
Sir, both A star and BB star are normal.
yes, that's correct. Now I ask, is this required to be A star and BB star to be normal? So the question is, I'm asking, is it always the case, like for any A and B, is A star and BB star are normal matrices? Let's see, what is A star? Star, which is A star star A and A star again. So A star is self-adjoint, right? So of course, self-adjoint matrices are always normal matrices, right? So even if A and B are not normal, what we can conclude is A star and B star are always normal matrices. In fact, they are self-adjoint matrices. Is there any other option true? Let's see. For AB to be normal, what do you need? AB star AB. So what is this? This is B star A star A B, and you want this to be equals to A B star, right? This is A B, this is B star A star. Hmm. What do we have? We have A normal. No, but from this we cannot conclude that both are same. We need the commutativity of A and B as well. So this is not true. Similarly, A B star would be normal. What about A plus B? Star operation is additive, so you get A star plus B star times A plus B, A star A plus A star B, B star A plus B star B. Now if I do A plus B times A plus B star, you can put this star inside. So you get AA star plus AB star plus BA star plus BB star. So this and this are same because of A and B are normal, but we can't guarantee these to be same. Hence, this is true. The fourth option is true if we have this additional condition that A, B star, and A star B commutes. The only correct option is option number 1. Okay, let's go with question number 2. A be a normal matrix, then which of the following is not true? So A has given a normal matrix. Then we have been asked about whether A can be written as PDP star, where P star is identity. Is this true?
Yes, sir.
Yes, sir. Yes. By what theorem? Or by what logic this is true? Can you explain? This statement in fact says that A can be or A is unitarily diagonalizable, right? That means there exists a unitary matrix P. This condition is called this matrix which satisfies this condition is called as unitary matrix. There exists a unitary matrix P such that A equals to P D P star, where D is a diagonal matrix. They haven't mentioned it here. D is a diagonal matrix. Then by spectral theorem, this is true. Spectral theorem. Is the spectral theorem taught in the lecture videos?
Yes, sir.
Yeah. So by spectral theorem directly we get that every normal matrix is unitarily diagonalizable. Okay. Now the second one, the range space of A is orthogonal to null space of A. Okay. Is that true? Does
Yes,
anyone?
sir.
Okay. How?
So there is a theorem which we in which we are using gram matrix is
Okay.
or
Gram matrix is something different. Gram is, I think, for any matrix A. If you consider like G as A transpose A, that is a gram matrix.
yes, sir, yes, sir.
But here we are talking
So
about the range space and null space of the matrix A itself. But I think something you can relate. Yes, 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 here. I think the range and null space of gram matrix is the same as null space of gram matrix is same as null space of A. But that's just more details. We don't need that much details here. We can do it in simple sense. Okay. What we want to show is null space of A is orthogonal to range space of A. Okay. Let's just take two elements. Let X belongs to null space of A. I'll write null of A. And maybe Y belongs to range of A. I'll write R of A. So that is, there exists some X dash belongs to, but A is from, okay, let's say Cn, such that Ax dash equals to Y, right? This is what means Y being in range. So it is inner product of X with Y. I want to show that this is 0, right? Claim that inner product of X with Y is 0. Then only X will be orthogonal to Y. So every element in the null space is orthogonal to every element in the range space. That's what we want to show. What is inner product of X with Y? It is X with A X dash, which is inner product of A star X with X dash. Okay. Now what do we know? X belongs to null space of A. That is Ax is 0. Now we have one result. It says that for normal matrix A, norm of Ax is same as norm of A star X.
Yes.
Yes. So what does it imply? What does it imply? That means if Ax is 0, then A star X also will be 0, right? Hence from here we get inner product of X with Y equals to inner product of A star X, which is 0, with X dash, which is 0. Hence X is orthogonal to Y. For every element X in the space of A and every element Y belongs to range space of A. Okay, this is the correct option. We want to tick not true, the one which is not true. Second one is also correct option. So for this question, that's the wrong answer. So option number C says if X is an eigenvector of A, then X transpose X is 1. This simply says norm X is 1. This is not a good option. For any eigenvalue, you
Because
can
of
find.
orthogonal vectors.
Yeah.
Sir, because of orthogonal vectors, norm is 1.
No. This is not true. X is just an eigenvector. See, whenever you have an eigenvector, any multiple of it will also be an eigenvector, right?
Yes, sir.
So we cannot directly say that it's the norm is 1. I mean, for just an eigenvector. You take an eigenvector of norm 1, I'll multiply it by 3. Now its norm is 3, and still it's an eigenvector. So this is a wrong
Understood, yes,
statement,
sir.
hence it's an correct option. But also option number 4 is correct. You can see a power k equals to 0 for some positive integer k. Need not be true always. I can just take identity matrix, still the normal matrix, but this is not true. So coincidentally, for this question, you have two correct options, option number 3 and option number 4.
Sir, please repeat the option number 4th, sir.
A power k equals to 0. This is the condition that's not always true, right? You take A as identity matrix, for example. Identity matrix is a normal matrix,
Yes, sir.
but it does not satisfy the condition number 4. That A power identity power k is identity for all k belongs to natural number, right?
Yes.
So it's never 0. In fact, the matrices which satisfy this condition are called as nilpotent matrices.
Yes, sir.
So the question is, now I'll ask, does there exist a non-zero nilpotent normal matrix? Can anyone answer this question? Take some time. This kind of questions will be asked in, I mean, if any of the crowd is preparing for PhD tests, interviews, and all, then in interviews they ask such questions. Uh, okay. Mhm.
So can we use here JCF
What?
diagonal block 0100?
Can you repeat again?
So I think answer is no, and I'm thinking by
Yeah,
Jordan canonical form.
yeah, you're right. The answer is no. There does not exist a non-zero nilpotent matrix. Okay, you are trying to do it with Jordan canonical form.
Yes, sir.
But you have something better. You have a normal matrix.
Yes, sir.
If you have a normal matrix, just now we have seen by option number A, it can be diagonalized. Every normal matrix is diagonalizable. Right? Think more. The condition that you have observed right now is all eigenvalues has to be zero, right?
Yes, sir.
And the second one you have observed is A is diagonalizable. I mean, if that's A, be such a matrix, A is diagonalizable. Then try to show how we can do A as zero. How we
So
can
the
prove A as
only diagonalizable matrix exists. Nilpotent matrix is only zero matrix.
yes, but how will you prove that?
Yes, sir.
No, no, how will you prove that in this is just a one line thing, right? Mathematically you have to be precise, right?
Okay, sir.
How we can say it is say if A is diagonalizable, you can find a matrix P such that A equals to PDP star here because it's normal, right? Now what are D? D will have diagonal entries which are eigenvalues, right? But here since all eigenvalues are zero, which implies D as identical zero matrix. Well then what will be A? P times the zero matrix times P star which is zero. So by using these two conditions directly we'll get the answer. Okay. Is there any doubt in this question?
No, sir.
Let's go to the
Sir,
next
in the
question.
lecture, sir was telling that importance of normal matrices. So why we have normal matrix so is so important, and in which sir was telling that Gram-Smith process orthogonalization process doesn't help in some cases, so that we need normal matrices. I didn't get it. So
In Gram-Schmidt, what? Like I haven't followed the lecture videos right now, so I don't know what importance he explained about the normal matrices. But there are applications of the normal matrices in numerical theory when people do the numerical analysis. Okay, I'll just tell you some glimpse of it, what it will be. See, okay, there is something called pseudo spectrum. Okay, what does it mean? For any matrix A, if you take some arbitrary small perturbation of that matrix, you multiply with, I mean, you add up some matrix so that the norm is still, less than epsilon. They are in the gap, right? not sorry, not this. A plus E such that norm of this E is strictly less than epsilon, and then you find the eigenvalues of this matrix A plus E, right? So what that means, if you add up some arbitrary matrix A, which is kind of small, a small matrix in your matrix, then how much the eigenvalues fluctuate, right? Are those eigenvalues same as of A, or like what much difference does it make, right? This fact will be useful in data analysis, right? Because when you have large data, sometimes some data gets fluctuated with a small amount, right? This amount. So always you have a fixed data A, and then you allow some perturbations, right? And but you want, because for any data you can kind of characterize all the properties by using its eigenvalues, right? What you want is, even if you allow some perturbation, the data should not change so much, right? In those cases, normal matrices has um, what do you say? Um, what's the word I'm looking for? Stability. Yeah. In normal, when you look for if you consider it as a normal matrix, then there are some formulas which will say you that under what conditions you can exactly say that the changes in the eigenvalues, which won't be so large. Okay. So the applications of normal matrices are kind of huge, but they are in different sectors in numerical analysis and some matrix analysis people do. Okay. Uh, I don't know what
Okay,
sir
sir.
told applications in lecture video, but this is kind of a glimpse. And this is kind of a most important type of all matrices, right? Because you can directly say that it's unitarily diagonalizable.
Okay, sir. In lecture, sir was telling that Gram-Schmidt orthogonalization process uh, doesn't help in the normal matrices. How, sir?
Doesn't help in normal matrices. I don't understand this
Yes,
statement.
sir.
Gram-Schmidt procedure is for converting a basis into an orthonormal basis, right? How does it relates to a matrix? I don't understand the statement exactly. See, you know the Gram-Schmidt basis, right? Procedure, right? Last time I have explained it in the session.
Yes, sir.
In that, there was no relation of any matrices. You just needed some vectors, and then you do the computations and find the orthogonal vectors corresponding to those. So I don't understand sir's statement. I'm sorry.
Okay, sir. No problem.
Maybe you can write an email to him and ask what he was
Sir,
referring to.
tell me your email ID. I was trying to mail you, but mail ID doesn't exist, sir.
My mail ID, I have wrote last time. I'll write again, but you better ask him, not me. I mean, his email ID, the professor, because what he said, I don't know, right? And he's not here. In fact, I'm in IIT Madras. He is a professor from IIT Roorkee, so we don't collab.
Okay, sir.
Yeah, you can find his email ID in maybe NPTEL course or in IIT Roorkee website. My email ID I can write here in the chat box. Just a minute. Yeah. Uh, yes, I wrote my email ID in the chat box. You can email me if you have some doubts. But for this particular concern, it's better if you email the professor directly. Okay.
Okay, sir. Thank you, sir.
Okay, let's move on to the next question. Which of the following matrix is positive definite? Okay, so definition of positive definiteness. A matrix A is called positive definite if and only if inner product of Ax with x is strictly greater than 0 for all x belongs to Cn which are non-zero. Okay, this is the definition, but practically by looking at this definition you can't just really say, like the definition is hard to verify. So we have some consequences. The first consequence is that A is positive semi-definite if and only if A is self-adjoint and spectrum of A, this is the set of all eigenvalues in finite dimensional case, is contained in positive 0 to infinity. This is the first characterization. Second is there exists a matrix P non-singular such that A equals to P star P. Okay. So let's see if we can do something from these. Even we can use this condition if you have some nice observation skills. See, okay, I'll tell something regarding matrix computations now that might be very useful in further. If you are going to do some work in linear algebra and matrices, maybe this thing will work. How do you compute this matrix multiplication? Let's say, okay, I'll take this matrix. This 116, 104, 649. If I just multiply with 1, 2, 3, right? How do you do this multiplication? You do this first row and then you multiply with the column, right? You take 1 times 1 plus 2 times 1, 3 times 6. Similarly, now for the second, you do this 1 times 1 plus 0 times 2 plus 4 times 3. Then you do 6 times 1 plus 4 times 2 plus 9 times 3. Right? Now I'm saying this matrix multiplication is in fact 1 times the first column plus 2 times the second column plus 3 times the third column. Right? You can observe it here. 1 times the first column, this is the first column, 2 times the second column, it's not in the nice position, but still you can see. Then 3 times third column, right? So this is always the case. If you have any matrix, you can write as the columns, let's say A1, A2 until AN are the columns of the matrix, and then you have a vector in Rn, x1, x2 until xn. Matrix multiplication is simply x1, A1, x2, A2 until xn, AN. So this fact will be very useful in matrix computations. Okay, try to adapt to this fact. Now if I do, let's say for this matrix, I want to do AE1, right? A this matrix 116, 104, 649. What is E1? 100. So by this logic, what will be this value? Just 1 times first column, right? Because for 0 times this plus 0 times this is nothing. 0. Okay. Do you understand this matrix multiplication? If yes,
Yes,
then we'll just we can directly say from here. See, what we want is inner product of Ax with x has to be strictly greater than 0 for all x which are non-zero. This we want. But if you observe the second row in this column is 0, right? That means if I, okay, that means if I do now AE2, what I get? Second column, right? By this logic again, I have explained here. If I do AE2 here, then I'll get 0, 1, 0. That means 0 times first column plus 1 times second column. 104. Now if I take the inner product with again E2, E2 is 0, 1, 0. So I get the middle element, the second element, right, of this vector, which is 0. Right? That means this option is not the correct one. because you have E2 which is a non-zero element, but inner product of AE2 with E2 is 0. We want it strictly positive. This is not positive definite. Option number D is gone. Can you find such a thing in any other options? Yes, Suraj Pathak, do you have a question?
So in the first option, 2
Yes.
minus 3 0 multiplying by 1 0 0 1.
What?
Sir, second option is correct.
Yes, second option is the correct option. That is a positive definite. Yes. How did you come up with
Yes.
that?
Sir, principal minor.
Yeah.
Uh, First five is positive,
And
and
then
then second 5 into 3 minus
yes,
9 is also positive,
and the
and
determinant is also
then
positive.
yes, also positive.
Yes, so that's another characterization. Yeah, that's correct. So option number three, which says that if all the principal minors are positive,
So 0, 3, 7 minus 1 take minus, then if modulus negative, so मतलब third option is not
yeah, the determinant is
active
negative,
defined.
right?
0, 3, 7 minus 1
Okay,
minor लेंगे
okay,
दूसरा स्थिति.
this one you're saying.
Then yes.
Yeah, correct.
So it's a negative modulus. So मतलब
Yeah, so
तो
this is
ये
also
third option
yes, this is also wrong
not
option. Yeah,
wrong option.
and for the first option, can you mute? There's so much of noise from your side. Thank you. For the first one, also you can see as the logic I have explained, AE3 you will get 2 minus 3 0, and now if you take the dot product with E3, you will get the third element which is 0. So this is also not the correct option. The only option left is option number 2, and that's the correct one. Okay, so let's go to question number 4. The matrix associated with the quadratic form, this is given by. Okay, first of all, this is a homogeneous second degree equation. So yeah, we have a symmetric matrix. All matrices are symmetric matrices. Yeah, so okay, you have to check. If we simplify x1 squared plus 3x2 squared minus 2x3 squared, so this guy here will give me x1 squared plus 2x1 x3 plus x3 squared plus this is 4x1 squared minus 4x1 x2 plus x2 squared. So collect the coefficient of x1 and we get 2x1 squared, coefficient of x2, 4x2 squared, coefficients of x3 minus x3 squared, and then x1 x2 minus 4x1 x2, then x1 x3 plus 2x1 x3, and then that's all. Yes. Okay. So how do you get a quadratic form sorry, a matrix associated with the quadratic form? You first find the second degree terms, the squares, x1 squared, x2 squared, x3 squared. Put those in the diagonal entries. Then you find the multiple terms, x1,
So
x2.
there's a
Sir, B
yes,
option.
one mistake, sir. Because
Uh,
6x1 square we are getting.
oh, sorry. This and
4x1
this.
4x1 is square.
Oh, yeah, sorry, I missed this. Is there any other mistake?
No, sir, I think.
Okay, maybe this is fine. Yeah. Yeah, thank you. So now I get 6, 4 minus 1, and then for x1, x2, these the coefficient will be divided into these two parts equally. So minus 4 upon 2, which minus 2 here, minus
Minus
2 here.
2.
This x1, x3, the coefficient is divided into these two terms, 1 and 1. We don't have any term like x2, x3, so it's 0. Which one matches? Option number 2. Okay, that's good. Let's go for question number 5. For a quadratic form, this one, which of the following statement is true? Hmm. Oh, damn. So one logic is you find the matrix corresponding to this quadratic form. What will be the matrix? It will be a 4 cross 4 matrix. X1 squared, x2 squared, x3 squared, x1 squared. So like 2, 2, 3, 4. Then you have x1, x4 term directly. There is no x1, x2, there is no x1, x3. x1, x4 is 5, so there equals 5 by 2 here, 5 by 2 here. This is 0, this is 0. Do you have x2, x3? No. x2, x4? Yes, which is minus 2, so there is minus 1 here. This one here. That's so this is the matrix. So you can directly find out now is this matrix positive definite. So if we do the principal minus thing, just a minute. Meanwhile, you can just calculate whether this is positive definite. Yeah. Okay. So did you get calculated? Is this a positive definite matrix? So you can say the leading principal minus, the first one is positive, and second one is 4 minus 0, it's positive. Then you have to find the determinant of this guy. It's just diagonal matrix, determinant is also positive, 3 times 2 times 2. Now you have to find determinant of the whole matrix. What will it be? So let's do calculate 2 times determinant of this matrix, which is 2 times 12 plus 1 times 3. Then plus minus plus minus minus 5 by 2 times determinant of this matrix. So determinant of this matrix, I'll get minus 2 times minus 15 by 2. That's great. So we get answer as 48 minus 6. So it's cancelled. Minus minus plus minus 5 by 2. What is this value? It's 42 minus 75 by 2. So I get 84 minus 75 by 2. Yes, it's positive. So all the principal leading principal, so all the leading principal minus are positive and the matrix is positive definite. Is this okay?
Yes, sir.
Yes. Okay, now question number 6. question is the inertia of the quadratic form is. What do you mean by inertia? Can anyone tell me?
Number of positive eigenvalue, common number of total number of eigenvalue positive with total number of negative,
Hmm.
total number of zero.
Yes, that's correct. So it's a three tuple. The first one is number of positive eigenvalues. The second one is number of negative eigenvalues. Third one is number of zero eigenvalues. So what do you mean by number of zero eigenvalues? That's algebraic multiplicity of the eigenvalue zero. Even when you say here number of positive negative eigenvalues, you also count the algebraic multiplicities. Okay. So naturally, when you talk about negative and positiveness, you kind of assume that the eigenvalues are all real, right? Why is that the case? Because for every quadratic form, you associate a symmetric matrix, right? In fact, a Hermitian symmetric. So for every Hermitian matrix or symmetric matrix, the eigenvalues are all real. Okay.
Yes, sir.
Yes. So because of that reason, we can define inertia for a quadratic form. So let's calculate the eigenvalues of this matrix now. For this quadratic form Q, what will be the matrix? Coefficient of x1 squared is 1, x2 squared is 2, x3 squared is 1. And there is no term of x1, x2, so these guys are 0. Then there is x1, x3 is 8, so 4, 4. x2, x3, there is no term, so this is the matrix. So now we have to find eigenvalues of this matrix. Can someone magically tell me the eigenvalues of matrix A? You can always look for some tricks to find eigenvalues of the matrices. For example, see here I can directly say that 2 is an eigenvalue. Also I can give you eigenvector E2.
So this option third is correct.
No, I don't know the answer. How did you find all the eigenvectors? Sorry, eigenvalues?
So determinant is a negative, so matrix is 3 by 3 order, so one eigen value is negative and two eigenvalues are positive.
Oh, that's true. Oh, that's smart. Good. So you have calculated the determinant. The determinant is negative, and the determinant is the product of three eigenvalues. So of course, none of them those can be zero. So option number two, option number three and option number four are gone. So only option number one and option number two are gone. Only option left is option number three and four. But if option number four, you get three positive eigenvalues, which will give you a positive determinant. So this is also gone. So option number C is the correct one. Oh, that's smart. But also I mean, this will be useful. How will you find eigenvalues? So the trick that I have, not trick, the calculation that I have explained some time ago about the matrices, right? Here you can see A E2 if I do, right? That means A times the matrix 0, 1, 2. What I'll get always, this is 0 times first column, 1 times second column, and 0 times last column, right? So what is the second column of this matrix? But you can observe this is again 2 times 2 is an eigenvalue. Then if you get one eigenvalue, you can directly say okay the trace. You can then it will be a quadratic equation. Right? The one eigenvalue is 2. Let's say other eigenvalues are x and y. Then this is the trace, which will be sum of diagonal entries, which is 4. And then this will be determinant. what is the determinant? Some guy calculated the determinant right now. Let's just calculate 1 times 2 plus minus plus 4 times minus 8. So 2 minus 32, it's minus 30.
It's 30.
So you get the product as minus 15 and sum as 4 minus 2, 2. So to solve these two equations, right? So just a quadratic equation now. You substitute this value here, or can you do that directly? Sum is 2, product is minus 15. What?
So 5 into minus 3.
5 minus 3, perfect. Sum is 2, product is minus 15. So the eigenvalues you have are 2, 5, then minus 3. So 2 eigenvalues are positive, 1 eigenvalue is negative. So you get option number C. That's the correct option. Okay, let's go for the next question. Let Q of x1, x2 is some quadratic form, then the equivalent diagonal form of the curve Q of x1, x2 equals to 1, 1, 0 is given by. So what do you mean by equivalent diagonal form? You just find the eigenvalues and find the matrix, kind of diagonal matrix, and write the what is it, quadratic form corresponding to that diagonal matrix. The matrix here is
Sir,
coefficient
is
of
it
x.
related to finding transformation of quadratic form?
What did you say?
Sir, is the question based on to finding the transformation in quadratic form?
The question is finding the first diagonal matrix and then finding the quadratic form corresponding to the diagonal matrix.
Okay,
From
sir.
A, you will find the diagonal matrix G that will be consisting of eigenvalues of A, and then from that diagonal matrix G, you will find the quadratic form, which will be a diagonal form basically because there won't be any this kind of multiple terms. So A is 8, 8, and then 6 divided by 2. 8, 3, 8, 3. Nice matrix. What are the eigenvalues? So, yeah, I can guess 8 plus 3. 11 is an eigenvalue. And then 11 plus x will be the trace, 16. So, x is equals to 16 minus 11. 5 is an eigenvalue. So, you get eigenvalues are 5 and 11. Can anyone tell me how I
Sir,
got
because
11 as an
row
eigenvalue?
sum is same, sir.
Yes, and what will be the eigenvector?
Sir, 1, 1.
Perfect. So now you have the diagonal matrix D as, let's say, 5, 0, 0, 11. So what will be the quadratic form corresponding to this? 5 times y1 squared plus 11 times y2 squared equals to 110. Or if I divide by 110, let's say, I get y1 squared divided by 5, 2 is 10, then
Sir, why we are using y1 and y2?
I don't know. They in the question they have asked x1, x2, but in the options they have written in terms of y1, y2. That's why I'm writing. But there is no much difference, and also no logic.
No, sir, I mean vector y1 and y2. Sir, I didn't understand this
No,
step, sir.
you can write x1, x2 there. There's no logic, no difference. They're just variable. That's the
Sir,
print
our
mistake.
first
In fact,
time
here
is to
they should
find
have
the,
written x1 and x2 squared. But because of that typo, that's the problem kind of thing. In the options itself, they should have written the x1 squared and x2 squared. But by mistake, they have written it as yi's.
sir. So our first time is to finding this diagonal matrix first.
Yes, yes, yes.
Okay, sir.
For any quadratic form, the equivalent diagonal form is this is how you find. You find the diagonal matrix, in fact, and then write according, yeah, diagonal form, quadratic form, in fact. And then this is just the curve, like they have given a kind of value of the function, and you just have to write the expression. What goes behind this all diagonal form and quadratic forms, maybe I can explain in the next time. So write it there. I'll delete
Okay,
something.
sir.
Okay, what's question? Kind of geometrical meaning of quadratic forms. Okay, just 1 minute. Yeah. So now, so what will be the correct option? Last one. Okay, let's go to the next question. Question number 8. The minimum of the quadratic form something exists at. Okay, okay, this is a typo. Here it should be exists. How come 11? I mean, this is 11 upon 110, right? This is 10, right?
Last option.
Yeah, last option. What's is there any mistake I did?
No, sir. I think, sir, he was asking how we can find this eigenvalue 11, sir, by row sum
Oh,
or
eigenvalue. Okay. So for any matrix A, if the sum of all the rows is same, then that will be an eigenvalue. Sum of the first row is 11. Sum of the second row is also 11. So 11 will be an eigenvalue. And the corresponding eigenvector will be all ones. See, I have explained some time ago how will you do the multiplication. That is even useful here also. What will you do if I multiply this? It will be 1 times the first column, then again 1 times the second column, right? But essentially, what are you doing when you add it up? You are summing up these row entries, right? 11, and then you are summing up these entries, which are 11 again. So this is again 11 times 1, 1, right? So 1, 1 is an eigenvector corresponding to eigenvalue 11. This you can do for any n cross n matrix whose each row sum is the same. Whatever the row sum is, that will be an eigenvalue, and corresponding to eigenvector will be all ones. Does that clear your doubt? Okay, maybe it's cleared. I'll go for the next question. Question number 8. The minimum of the quadratic form is. So the standard form of the quadratic form is given by x transpose some kx plus or no, either it is minus 2fx something plus c. Okay, I think is this correct? This is the standard form.
XT होगा सर 2F XT
X transpose you're saying? No, but then that's a problem. F I'm considering as a row vector, like then only if I multiply with column I'll get a number. F is a row vector.
okay sir
Or maybe I'll say F transpose. Is that okay now? Because then usually F will be a column vector. Now F transpose is a row vector. Yeah, this is fine. This is fine. Minus 2 F transpose X. Okay, if I compare with this guy here, here the K will be a symmetric matrix. So X transpose KX will give me an expression which is a homogeneous second degree equation. Right? So I'll collect all the homogeneous second degree terms. This is this. Everything else is not homogeneous. So from this I'll get K. X1 squared is 3, then x2 squared coefficient is 2, x3 squared coefficient is 5. Then x1, x2, -1, -1, x1, x3, 1, 1. There is no x2 term. Okay. This is my k. Now I need the linear terms, which are this. Now if I take -2 common, because it is here, they can write this as 1, 2, then 3 times x1, x2, x3. Right? This is -2x2, -4x2, and then -6x3 is perfect. So this is my F transpose. And then at the end, the C scalar number is 9. Okay. So we have found, we converted this question into the standard form. And then, you know the formula. The minimizer x star is given by K inverse F. Okay. So F will be a K inverse will be a 3 cross 3 matrix, and then F will be a column vector 1, 2, 3. Okay. I hope you can do it this now. This is simple calculation. I don't know the answer. I'll leave it to you as an exercise. Hmm. Okay, let A be 4 cross 4 matrix with minimal polynomial this. Then the total number of Jordan blocks in the JCF of A corresponding to all eigenvalues is. So the theory that we'll use is number of Jordan blocks corresponding to eigenvalue lambda. Hmm. Okay, I'm confused. What does the degree of the factor x minus lambda in minimal polynomial represent? Is it the number of Jordan blocks, or is it the geometric multiplicity of the eigenvalue lambda?
Jordan blocks.
Number of Jordan blocks. Okay. No, but no, I don't think so. No.
So repeat the question one.
No, something is wrong. What I want to ask is, see, you can write the minimal polynomial. See, MA of lambda. This is minimal polynomial. It will be like something like this: x minus lambda 1 to the power r1, then x minus lambda 2 to the power r2, until x minus lambda k to the power rk. Right, where lambda i's are kind of distinct roots, and r1, r2, rk are algebraic multiplicities. Sorry, not algebraic multiplicity. This is just degree. You want to see that 8 question again?
Okay, sir.
Okay. Yeah. So this in this way you can write the minimal polynomial always. My question is, what does this Ri represent? So the guess is that R1 is equals to the maximum size of a block corresponding to eigenvalue lambda 1. This is my guess. Is it correct? If you don't know about it, let's come back to this question after the question number 10. Maybe in this we'll get an idea. Okay. So we want to find the Jordan canonical form of this matrix, and the available options are these four. As you can see in all the options, the diagonal entries are all 1. That means the only eigenvalue is 1. The question only remains that what is the geometric multiplicity? Right? How do you calculate geometric multiplicity? I want to calculate the null space of A minus lambda, A minus I, 1 I in fact. If I do a minus I, I'll get 3 minus 2, 3 minus 1, 2, 2 minus 6, then 1, 1 minus 3, 1, 1 minus 3. So nullity
2, sir.
of a minus I will be 2, right? Okay. But what can I conclude from
Sir,
it?
B option.
So if I say option number B, then what are we concluding? That nullity, sorry, geometric multiplicity is the what do you say? Maximum size of a block, right?
Yes, sir.
Yeah, so geometric multiplicity of an eigenvalue is the largest size of a block, of a lambda block in the canonical form, right? And what will be the minimal polynomial for this then? If I compute, is this x minus 1 squared? Because in my claim, 2 should be maximum size of an eigenvalue. But something is wrong. So the minimal polynomial is simply x minus 1 cube is the minimal polynomial. Just give me a minute. Someone please confirm for this matrix A, what will be the minimal polynomial? Oh, wait, sorry. I made calculation mistake. This should be 4 plus 2 minus 6. That is 0, yes. And then again this has to be 0. Oh, yeah, that seems true. Okay. Minimal polynomial is x minus 1 squared. Mhm. Yeah, coincidentally, in this case also it's coming that geometric multiplicity is the same as the maximum size of a block, but that's not true. What I recall the best is that maximum size of a block is the degree in the minimal polynomial, and number of blocks corresponding to eigenvalue lambda is equals to geometric multiplicity of lambda. Okay, let's see what happens in identity matrix. For identity, eigenvalues are only one. How many Jordan blocks you have? You have three Jordan blocks. This each one is an Jordan block. And you have a minimal polynomial as x minus 1, right? So the degree is 1. Yes, so 1 is the maximum size of a block corresponding to eigenvalue 1. Yes, that's true. And how many blocks are there? There are three blocks, and for eigenvalue 1, you have three distinct eigenvectors, e1, e2, e3. So geometric multiplicity is also 3. And that's perfect. I think this is right. Okay, this is a correct statement? If I write minimal polynomial as these factors, then the degrees R1, R2, Rk represents like this. Ri basically is the maximum size of a block corresponding to eigenvalue lambda I, and number of blocks corresponding to lambda is equals to geometric multiplicity of lambda. Okay. Now let's come back to this question. What is the minimal polynomial given? This is x cubed minus 3x squared plus 2x minus 6. If you factorize this, I think this is x squared plus 2 times x minus 3. Is it correct? This is x cubed minus 3x squared plus 2x minus 6. Yes. Okay. So from this you can conclude what are the eigenvalues? Plus minus 2i and then 3. Right? But I can write this as x minus 2i, x plus 2i, and then x minus 3. So degree of every polynomial in every eigenvalue in the minimal polynomial is 1. That means maximum size of a block corresponding to an eigenvalue is 1. But matrix is 4 cross 4. So how many blocks you will get? You will get total 4 blocks, right? For every eigenvalue you get 1 block. And then there is another eigenvalue which is one of these 3, but you get only 1 block for this eigenvalue as well. The total number of blocks are 4. So the correct option is option number 4.
Okay, sir.
So is there any doubt in any of the questions?
I have a doubt in the previous assignment in first question.
A previous assignment. Assignment in the sense the one that I explained or the one that is there in the
Sir, the
session?
latest assignments which we gave, sir, last week.
Okay, I haven't seen it, but can you tell the question? Maybe we can try it here. I don't have a question with me.
Okay, sir, I'm telling.
Perhaps, sir, let A is equal to 1 minus 2 0 minus 2 1 minus 2 minus 1 2 0 2 0. Then the
Oh,
range of eigen.
What is A?
Sir, A is equal to first row 1 minus 2 0
Hmm.
and second row minus 2 minus 1 2
Hmm.
and third row 0 2 0.
Hmm.
Then the range of eigenvalues lambdas of A is.
Yes, sir. That's the question.
Range of eigenvalues. And what are the options?
Sir, first option is minus 1 is less than equal to lambda is less than equal to 3.
Hmm.
And second option is minus 5 is less than equal to lambda is less than equal to 3.
Hmm.
And third option minus 2 is less than equal to lambda is less than equal to 3. And last minus 1 is less than equal to lambda is less than equal to 2.
Okay. Oh, then this is simple application of the Girish-Goran's theorem, right? Is it? In Girish-Goran's theorems, what do you know that?
Sir, we get mod lambda is less than equal to 5.
Yes, sir.
The maximum row sum. What is the row sum? This is 1 minus 2 minus 1. I mean,
5, sir. Oh, yes, sir, 5.
so you just
And
take the
column
row
sum
sums,
also,
right?
right?
Not the
Yeah.
modulus of the sums. You just take the row sum, right?
Yes, sir.
Minus 2 minus 1. Then you take minus
No,
1.
sir, we are taking modulus of row sum, sir.
Yeah, so like 1, 1 and 2, right?
So first row sum is 3.
Sir,
And
3
second
and
row sum
second
is
is
You
5
take the
and third is
sum
3.
of moduli.
modulus of
Yes, sir, moduli.
each
Sir.
member of row.
Oh, okay. So then 3. Then this
5
is
and 10.
5. And this is 2.
Yes,
Yes.
sir.
So maximum row sum, it cannot exceed
yes,
5, and then you
yes,
take the row sum.
and
Maximum is
also column
3.
Column sum also, sir, 5.
5.
Can't exceed to 5, sir.
It's 2.
So minimum of row sum and column sum
Is 5. Yeah.
is
So the
5.
answer
5,
should be like
yes.
modulus lambda less equal 5.
Yes, sir.
So this has to
Range
be
is
the
between
answer.
-5 to 5.
Yes. There is no such option.
No option. Yes, sir.
That's true. What do they give as an answer?
Sir, B option.
Do they give any explanation?
Sir, the explanation which they gave,
Yet,
I didn't understand, sir.
What is the explanation that they gave? Let me check. Hmm. The assignment for solutions has been released. Assignment 4, right?
Yes, sir, assignment.
Oh, what is this? Mod lambda minus 1 less equal to implies. Hmm. Is there any another version of Kerensky-Corin's theorem?
No, sir, it's a corollary, sir, where we can use to draw a circle with the help of the range and to also center and some radius.
Because what looks like is what they did in the solutions is they take lambda minus diagonal entries. Like for example, in the first row, the diagonal entry is 1, right? Mod lambda minus 1 is less equal the sum of the other elements. Okay. And like, okay, I'll write it here. What they did is they took lambda minus 1 modulus, because 1 is the first diagonal entry, is less equal the sum of these two. Then they take lambda minus the second diagonal element, less equal the sum of these two, modulus and sum. Then lambda minus third diagonal element, which is 0, and then this has to be less equal sum of other two. This is how they did, and then they come up with the fact that for this equation, this is the condition. And similarly for this you get. Similarly for this you get. And in these three conditions, the maximum lowest bound is minus. But what is this?
Union of all these, sir.
Yeah, yeah.
So
Yeah, but even in this situation, the right answer should be minus 1 less equal lambda less equal 2, right? Even in this case, see, lambda has to be greater or equal minus 1. Here, it's greater or equal minus 5, minus 2, but which is the nice bound? Minus 1 is the nice bound, right? It cannot be less than minus 5, so there is no point in saying this. And it has to be less equal 3 and less equal 2. So which one you choose? Less equal 2. So this should be the right answer according to this logic also. I don't know how they arrive at this logic. Okay, I'll check with this solution whatever it is, and I'll explain it in the next session also again. Okay.
thanks.
This
okay,
is
sir.
question
Sir,
question
I have
1 in
a
assignment
doubt in the lecture, sir. What is generalized eigenvector of a quadratic form?
of a quadratic form.
Yes, sir.
basically generalized eigenvector is for matrices. Eigenvector is simply a non-zero element x such that A minus lambda I times x is 0, right? Then x you call as eigenvector corresponding to lambda, right? Eigenvalue lambda. But instead of just A minus lambda I, if there exists some number r such that A minus lambda I power r times x is 0, then we called x as generalized eigenvector corresponding to lambda. Okay. But then for a quadratic form, you just find the matrix of the quadratic form and find the generalized eigenvector for that matrix. That will be generalized eigenvector for your quadratic form. An example is maybe you take this as your matrix. So the A times 1 0 is 1 0. So this is an eigenvector. But what if I do A square times 0 1? What is A square? No, sorry. What I want. Okay. That's not a nice explanation. Eigenvalues are only 1. So A minus I times the vector 1 0. What do you get? A minus I is 0 0 0 1 times the vector 1 0 is 0 0. That means 1 0 is an eigenvector. Now what is A minus I squared? That is 0 0 0 1 squared, which is whole zero matrix. Now if I do A minus I squared, any vector, in particular I take 0 1, this is 0. It means 0 1 is a generalized eigenvector corresponding to eigenvalue lambda.
So 0 1 is the generalized eigenvector.
Yes. In fact, each eigenvector is also a generalized eigenvector because R you can take as 1, but not the converse. Every eigenvector need not be a generalized eigenvector. Every eigenvector is a generalized eigenvector, but a generalized eigenvector need not be an eigenvector.
Okay, sir.
Right? Because 0 1 is a generalized eigenvector, but it is not an eigenvector.
Okay, sir.
Yeah. Do you get an idea?
Yes, sir. Yes.
Okay, is there any doubt? Any more doubts?
Yes,
If
sir.
I
There is a
yeah.
proof of a theorem, sir, which I didn't get, sir, that Gram matrix is positive definite if and only if kernel of A is 0.
Okay, so Gram matrix is
Is
positive
positive
definite.
definite if and only if kernel of A is 0. Yes.
So Gram matrix let's call G and it is written as A transpose A, right? Okay, so we can try right now. If and only if, right? So let's say G is positive definite. We want to show that kernel A is 0. Let's see how we can proceed.
Yes, sir.
Let's assume whenever there is an if and only if statement, you have to go both ways, right? Once you assume this condition, then prove this condition, then you assume this condition and prove this condition.
Yes, sir.
So we'll go this way first. Let G is positive definite. That means inner product of Gx with x is positive for all x. Now let x belongs to kernel of A. Right? I want to show that x is 0, then we are done. Right? So if x is in kernel A, that means Ax is 0. Now what is Gx with x? It is inner product of A transpose A x with x, but this is simply Ax with Ax because the transpose operation goes there. I hope they are taking the real matrices. Now, yeah, now this is just because Ax is 0, right? This is 0. But since G was a positive definite matrix, this can only happen for x equals to 0. Yeah, do you agree with this argument?
Yes, sir.
one side is done. Now let kernel of A is 0. We have to show that G is positive definite. Yeah, I mean, this is the exact argument, no? Like, what is Gx with x? The same logic, I'm writing it here. Simply. This is inner product of ax with x, ax at the end. This is simply norm ax squared. So, you know, by definition of norms, this is always greater or equal 0, and this is equals to 0 if and only if ax is 0. And this happens if and only if x belongs to kernel of A, which is singleton 0, which implies x is 0. Don't know, there's which part did you not understand in all this?
So the first one,
Which one?
so that let G is a positive definite matrix implies
This is the definition of
this will
positive
be.
definite matrix.
So actually, I'm not at good in writing the proofs. So
Uh,
if you have any suggestion for me, then
just practice more proofs, read more proofs, and you will get how to do it. Because see, what I wrote here in the first step is just the definition of a positive definite matrix. Right? If G is positive definite, then this should happen, right? And then if I take an element from kernel, then I get that Gx with x is 0. But from the definition, what I know is this can only happen for a 0 vector x, right? This cannot happen for any non-zero vector x. Then hence I implied that x is 0. So ultimately kernel became 0. Right? So this was a very
okay,
easy argument. You just have to, like practice reading more proofs, maybe doing more proofs that will improve the proof writing technique. Okay.
okay, sir. Thank you, sir.
Yeah. Yeah. So if I recall all the doubts, now I have to explain question number 1, assignment 4. Next session, I'll take question number 1 in the assignment 4.
And
And
sir, geometric meaning of that.
what? Geometry meaning of quadratic and diagonal forms. Okay. Okay. So thank you for attending today's session. If there are no further doubts, we are done for today. See you all on the next session Tuesday.
Okay, sir. Thank you.
Thank you,
Thank
sir.
you.